Hi, my name is Thomas Remza, and this is my constant velocity lab for Physics 2211. For an introduction, the purpose of the experiment was to observe the motion of an object with the same speed without changing directions, and after this, to collect data and compare it to a computer-generated model which would plot two plots of data which we could contrast to determine if the velocity was constant in the experiment. As for our model, we had a system being a tennis ball that would roll across its surroundings, in this situation being the lab desk, and covering the primary physics content of this experiment, which was Newton's second law, which indicates that force is equal to mass times acceleration, which can be rewritten as force is equal to mass times the change in velocity with respect to time. But if the change of velocity is zero, that implies there's no outside forces and we can predict the motion, and additionally it could be rewritten as position equals velocity times time plus the initial position. Alright, so through our setup we would roll the ball across the camera frame, making sure that it stayed centered and at a constant speed, and we would also set the reference point of the ball in the tracker software to be the standard diameter of a tennis ball. From here, we recorded keyframes of the position to record data onto a plot of a position and time graph and find the initial conditions afterwards. From our data, we were able to pull an initial position of 8.44 times 10 to the negative fourth meters, and initial velocity by taking the average position from the second and first data points and find the total time being 0.533 seconds.
Oh, too fast, no?
That's fine.
No, I think that.
After putting the video into Tracker, I shortened the clip to minimize accelerations and possibility of after being pushed, and set the axis and starting frame at the center point of the ball. After that, recorded the center of mass at each point, each keyframe of the video to plot the position, and set the mass of the object to the standard mass of a tennis ball. In our computer model, first we use the starter code and input the mass, initial position, velocity, and total starting time, which would have been 0, and the initials described prior. Then I would specify the time increment with delta t, where it would be measured, and using a while loop in Newton's second law, it would calculate the position and velocity starting from the initial conditions by the equation specified above in the top right. To do this, I fixed both equations to follow the conceptual equations that had been mentioned before. Assuming the force vector would be 0, the velocity should be constant. From the model, it produced a constant rate and plot of a straight line, but the experimental data does not show the same. After a while, past the beginning of the experiment, it starts to dip down, showing a decrease in velocity over the course of the experiment. This could be due to a lot of things, mainly outside forces like friction or air resistance, or some user error, as there appeared to be some small bounces in the video. As for a what-if statement, what if the axes were flipped when we were taking data? In this experiment, conceptual outcome wouldn't change, but it would affect what component is being described as velocity. What does this lab mean, right? The two forces that would be present if the ball was moving at a constant velocity are the gravitational force that acts between the ball and the earth, and the normal force produced by the ball and the table interacting. These two would actually cancel out, saying net force would be 0 in the y direction, and given constant velocity 0 in the x direction. Even though it's not accounted for, friction, air resistance, and other forces may have been present in this experiment. In conclusion, in a perfect isolated system, there would be no outside forces on an object's motion that is presumed to be at a constant speed. And we can gather that there is another force present in this model, as the experiment results displayed that it travels less distance than the presumed model in the same interval of time. As for conceptuality, the Newton's second law can be helpful to predict motion, but all forces need to be accounted for in the system in order for it to be perfectly accurate. Thank you.